както винаги ще го направим на английски, така че ако нещо има, ще се опитаме на английски да обясним, ако не, ще се свършим на български. И така че не се притеснявайте да зададете въпроси, даже и да са... Ако нещо не е ясно, просто тези. So welcome to the 6th Blockchain Developers Meetup. Today we're going to talk about joint-oriented programming in Solidity Smart Contract. This is kind of tricky thing to do, and it was shown recently in one CTF, which is sort of hackathon in China. Basically, it uses some tricks to mislead the execution of a smart contract, and we'll see how that goes. But as usual, first we're gonna see what recently happened, and I believe this is the one and most interesting news from this month. So we were all expecting the Constantinople fork to happen on the 15th of January, but a few hours before the block for this fork, Chain Security, a company which is dedicated to research and security of smart contracts and blockchains, found an issue, which was, long story short, Constantinople now was meant to introduce a few new Ethereum improvement proposals, one of which is 1283, I believe, if I'm not mistaken, which will lower the cost for S-Store opcode, meaning it will be cheaper for saving data on chain. But for now, calling transfer function uses 2300 gas, and if this improvement proposal is passed, it will lower the cost of the S-Store, and it can introduce some vulnerabilities of some smart contracts. So that's why they postponed the Constantinople fork, and we were expecting it to happen some, let's say, February. That's what they told everyone, but we'll see how that goes. They postponed it with a month to have enough time to research further and find some way to fix this, because basically it introduces reference attacks for some contracts. So that was the introduction. Now we're gonna see directly this thing, and I'm gonna sit down. So this AcoraidaMonica game contract appeared in one of, as I said, CTFs, which are contests for kind of hackers, and as the blockchain challenge, this was the thing they got prepared. The idea here is that we have a smart contract, and we need to extract whichever money and ethers it has. So we'll start exploring the contract to see what exactly does it have and how can we do this. First thing we see is the hard-coded and hard-coded constants, which are strings, and it looks like normal thing, but here we have some weird string and logger contract where we basically have to log something. We'll see it later. We have a weird constructor here, which is doing some jump, and if you don't know, this is how we write assembly in a smart contract. So I assume you've seen it at least once. Then we have a modifier here, which is only human, and it's used in this function here. This only human modifier basically checks with this line of assembly code whether the caller is a human or a wallet only, or whether if it's a smart contract. This subcode Xcode size returns the size of the code of a certain address. So if you publish a smart contract, you know that addresses in Ethereum are the same for wallets and the same for contracts, but in the EVM, if the address is a smart contract, it has some size in the code property. So this is how we check if it's a smart contract or it is a human. And yeah, if it's not a smart contract, we'll see the size to be 0, so the modifier will continue execution of the function. The thing here is that if we check this Xcode size in the documentation, it's kind of misleading because we cannot count on it to provide the exact same check every time, because if we have a smart contract that it's not yet deployed, during the deployment we can call another contract from its constructor, and then the size of the contract that is the caller will return 0 before deployment. So this is kind of tricky, and this is one of the things that that is used here. And we have few functions. One of them is the start function, which is being passed two strings, the question and the answer, and the function is payable. So this will be a function probably called by the admin at the beginning of the execution of the smart contract, and this is the new round if somebody answers the question, to have another round with the second question. And this will be the function that will be looking mostly. This is the function that we are supposed to provide the answer for certain question, and if it is correct, and if we send 1 ether, if we follow the code, we probably should have the address balance transferred to our address, and then the logger should log something. Yeah, should log our address as a winner. So everything looks good, but now we need to see the logger address, and the logger contract, which is here. And now we stumble again on some weird stuff. We have here a hash of some string, and again hash of another string, and some weird assembly stuff to save some values on particular keys on the stack, which can be done easily without using assembly. We have here also a modifier, which is only owner, and again some functions. And this one interesting function, which will be the delegate forward. So if we call some function that it doesn't exist, it will go to the fallback function, and then the fallback function will execute this function with the parameter of the implementation, which will get this as a value for the address. So here the assembly is not that hard to read. It basically delegates code to some address, and this is a common practice to use when we need to have some sort of proxy contract. For example, as you know, if you deploy a contract, it cannot be changed, but there is a common practice to create some proxy contract with the logic of some smart contract or some library we can then change in the future. So basically this is what this does. It delegates the call to another address and checks the call data size. So it possibly counts to be presented the exact call data size. It's expecting exact call data size. And we have here the cases. Okay, and this is the logger, which is nothing that tricky. We only have 3 functions which only emits events. So this will be the thing that will announce if somebody wins. We can try compiling this contract, but as we don't know what exactly parameters were passed here, I'm gonna comment out the constructor and compile. So we can try running it. Now we have the compiled smart contract, and we can add here the start function the first question and answer, and we can try executing this function, the answer is, with another address while providing 1 Ether, for example. And we see this reverts. So this is something that we need to look through. This is where the magic happens. Obviously this transfer is not happening, and obviously it's something with this. We can debug it and see what exactly happens. So first the modifier is checking whether we are human or not. Then it continues the execution here. It checks whether the hash of the answer is the same as the answer that it is expecting. And then if the value provided is enough, this 1 Ether. So then again it saves our address to the questionnaire variable in the smart contract, and then it should transfer the smart contract balance here, but it reverts here. So this was the tricky part, and some guy that was participating in this CTF, he created a deep explanation of what exactly is happening here, and I'll show you what the resolution is. First thing that he found out is that if we, I don't know how many of you know that how exactly functions are working in a smart contract, but basically before execution, when the smart contract is deployed, functions are it's being calculated their SHA-3 hash, and the first 4 bytes are representing their basically their name. So the whole smart contract works like big switch case statement, and every function is called by the first 4 bytes of the hash of the function with the parameters. And here,
what is the purpose of this logger?
It turned out that it was put there for misleading, okay. But now we'll see why.
Okay.
Okay, so here we see if we calculate the hash of this upgrade address function here, it is the same as this function of the logger. We here have the first 4 bytes exactly the same. So when we call this function, we're basically calling here the upgrade function of this smart contract, and we are changing the address here. This is one of the first things that happens here, and then we can, after compilation, we can get here the opcode, the bytecode of the smart contract. And we can see it, what happens as a opcode, like what the logic is. So here it was push 8, okay. We have here a check whether the hash is matching with this, and we are checking also the call value if it's 1 ether. And then we have this weird jump test, which is jumping somewhere. We can follow this using, for example, let me see. Okay, I have it here. Okay, so here this jump is jumping here on, I don't have exactly the address, but it's jumping here and it's checking whether the call size, the call data size is matching some value, and if it's matching, it's getting here and it's pushing something to the stack, which is this, and the caller address here, then pushes again FFFF, and it's making binary AND, which basically adds FFFF to the caller's address and gets the last 2 bytes. So we can have here arbitrary code executed with manipulation of the address, and again then it's jumping somewhere else. The interesting stuff here is that we don't have withdrawal function, and we cannot count on the transfer that is here because it jumps somewhere else. So in order to get the balance here, we need to execute call or delegate call somewhere else in the smart contract, which can happen only if we have this opcode F1 or F4, which is call or delegate call. The next thing that we see when we get the smart contract opcode is this weird stuff EBZZR, which is, if we check, it's used for encoding the metadata hash of the bytecode of the smart contract, and we can see that we have a jump test and a delegate call with this metadata hash. So we can jump there. And it's time for us to see how the constructor takes place here. We are here setting a program counter and then adding something to it in jump, which basically jumps here and adds the withdraw function pushes this to the stake, which is exactly the signature of withdraw function. So this is what the constructor or the smart contract is doing here, is in its weird assembly. Okay, and then it's time for us to see where we can jump for it, because in order for us to call the withdraw function, we need to jump from here somewhere else, then to the withdraw function, and then to somewhere where we will end the call with the needed value of 0, which is the something which is expected to happen when we end a transaction. If we have something different of 0, it means it will be reverted. So the next thing we do here is we can see this weird string, and it turns out this opening bracket have the same exact binary code of the jump test, which is 05D, if I'm not mistaken. Okay, and we now have a clear plan how to handle this through. We need to have additional smart contract created, then we need to brute force an address which is matching the condition for the binary at. So the last few bytes of the address should match where we need to jump in order for us to execute this here. Okay, and okay, here. This is what the guy decided to do. He created this smart contract with the hard-coded addresses of the player in the game, and then he calls withdraw function, which calls transfer with the on the game address. So a delegate calls there. But in order for it to return 0 and the transaction to pass through and not be reverted, it needs to return something here. So this this thing that is returning from the function, it's being called. It's being passed here. After the call and the at here, it jumps to 0x98, which is another address here, and then the next is 099, which is stop. So the stop calls the fallback function and it exits with 0, and this is the transaction can pass through. Now we will see it happen in practice. So in order for us to test it, I have here all the smart contract needed, which I'll provide you to check it further. And we need to start our self-private chain, for example, local get. We can do this. Let me get my stuff here. Okay. So first we need to initialize where our blockchain will be stored. And we provide a Genesis JSON, which is basically describing how our blockchain will be looking. We have here the chain ID and some other configurations of our chain. We have the Coinbase account, and we have the difficulty set, the gas limit, and some pre-funded addresses which we're gonna use for these calls. Okay, now we have defined our blockchain, and we need to start it. I've prepared here an execution line. Okay, so now we have a running. Okay, we have a running network, and we need to attach it. Okay. Okay. This stuff happens. Okay. Weird thing. Let me check if I don't have something running. No. Okay, well, we'll Google it. Okay.
We can just remix that, no need to have a call over it. Just as
Yeah, but we need to have. I've prepared here a note. Okay, I'll walk you through. We have here a deployment script, which basically will deploy the correct data for the logger and the smart contract. So that's why we needed a local testnet. But
do you have Java or something?
I have. I can try there.
And then just click on
But we cannot predefine here the addresses. We need the private chain. The thing here is that in this smart contract, the particular smart contract is counting on the on this address, and we don't have the private keys for it, so we cannot add it to the trouble. Okay, we'll only walk through the code.
Can't we change this?
If we changed it, it won't work. It's counting it for the hashing and for everything else. So, okay, we have here a deployment script, which obviously we cannot run, but here in these calls, we are basically deploying these smart contracts that we looked at, the logger agent, the logger, and this big thing is the AcoraidaGame contract. Okay, and then we have here a transaction which is updating the address for the logger, and then we have a transaction here that we need to execute in order to start the contract where we tried with the question and answer. And the solution for this that we walked through is this data, which basically is a transaction data to the smart contract function. We saw here the answer is to this function. Okay, here, and with this payload. So this is the answer, which is binary formatted, and here we have the answer length, the answer, which is here provided the letter R, and another thing of the payload is for the delegate call, we define here some other bytes in order to have the correct checksums and hash. Here is what happens in the constructor of the smart contract. So this call basically happens here. Okay, I don't have it open. It happens here. When we have this smart contracts deployed, basically executes here this function. Okay, and we pass here the value, which is the required 1 Ether, to the smart contract of the game. We have here additional stuff for the gas limit and other things.
Sorry, can we view the get command one more time?
This?
The dash command. No, is there a port somewhere that you
No,
can specify?
only network ID. But I don't believe here.
Can you change the network ID to something else?
Again, same thing. I tried it a few hours ago and it worked, but obviously.
Here's the port 30303. Most probably it's taken. There's a process.
I can try rebooting the machine later and execute the script. Okay, so this transaction basically is doing, and it's adding some padding here. This transaction is basically what I showed you here. It's adding here it's being executed first from an address that is chosen carefully, which was brute forced to match these two last bytes, 05E6, and then we have this 4B1, and this return here we have from here. So when it makes the addition, it gets 98, and then what I told you, it goes to the fallback function and then executes. Yeah. So basically that was it. Unfortunately, I wasn't able to show it in action.
Shit happens.
Yep. And now.
You can probably share with us all the links to the actual videos that the guy did.
Yeah.
So the things German do. And
Yeah. He's.
Try it out.
Yeah. Actually, the guy that cracked this, he has a YouTube channel. His name is LiveOverflow. So the credit goes to him. And yeah, thanks. Now I'm gonna try reboot and execute it, and we can continue chatting.
In your experience so far, have you ever encountered anything like that in practice? Have you ever encountered an issue like that, an act like that?
I haven't encountered anything, and I obviously wasn't thinking it was possible until I saw this.
Yeah,
But
it's pretty odd. I mean, it's only a concept that you have to name it for actual most programmers actually.
yeah, if you, I don't know, in my opinion, it can happen, and it can be like used for malicious purposes only. So when we are doing smart contract audits, we need to look deeper into this. So because only like in this case, particular constant string can do much more shitty things.
There's some tools that you paste the smart contract and etc. Have you tested this?
I haven't tested this particular smart contract.
Okay, I'll be interested because most of the times they they're not very efficient.
I'm not quite sure if it's gonna show something, because the actual thing happens in the constructor of the smart
Exactly.
contract, and if we don't have the exact payload that is passed there, we don't have the same smart contract, because we saw that there in this smart contract the withdraw function is being added into the constructor call.
Mhm.
Okay, let me try that out. Mhm. Same thing. Okay. Without this. So yeah, sorry for not showing a demo. That was basically it.
Thanks, man. That's really good. Thank you.
Thanks again for everyone showing up. Сега можем да видим по-неофициално вече на български.